wanted to have a particularly high-profile kind of Dean's series, and we're still kind of figuring out the details, but it just so happened that our speaker today was available and in town, so we thought, well, let's try with this, see what happens, see how many come, and lots of people came. So it's my great pleasure to introduce Bran Selić, who will probably be a name familiar to most of you. He's extremely well known in the kind of model-based software engineering field. You know, he's got a background in starting his own company. It's a very successful company, Object Time, that really influenced the field. That led him to be a IBM Distinguished Engineer, where he took a leading role in defining UML 2.0, so he's the person to blame if you don't like UML. And now he's running his own consulting company, and I've known him for very many years, actually, and it's a real pleasure to have him come and speak to us at Monash. So I'll pass the floor over to you, Ben.
I wish he hadn't mentioned the UML angle, but yes, it is true, I am partly responsible for UML, although how many of you actually like UML? And I look at this. Oh, there's some people who, how many of you hate it? Honestly, come on, be honest. There's lots of things wrong with the UML, by the way, but I can tell you what they are. They're usually not the ones that you think that are at least popularly raised against UML. Anyways, it's really great to be here. I'm thankful to John and the faculty here for giving me this opportunity to talk. I'm also very pleasantly surprised by the number of people, which is, by the way, why I asked that the doors should be locked so that nobody leaves before the end. I love Australia. I'm new to Monash, but I do have a Monash badge here, so I'm partly sold. And I hope you can listen quickly because I have 76 slides and I have 45 minutes. I won't, of course, I should finish in 45 minutes, or maybe 46. I'll try and give you a sense of what's happening. This is a talk I've given to industry, a number of industrial organizations. And by the way, I'm from industry. I did my first program in 1968, so you can see how old I am. One of the interesting things about that, by the way, is that the way software development is being done today, in the vast majority of cases, is almost the same as it was done in 1968. Good heavens, right? It's kind of scary, isn't it? So we really need to do something, and this is part of the intent here. Part of the intent behind this talk is to perhaps encourage people to be more open-minded and understand what's happening in industry with this thing called model-based engineering or model-driven development. How many have heard of the term model-driven development? Okay, how many? Yeah. It's a bad term, by the way. Yeah, and I'm using it here. He says, I call it model-based engineering because models don't drive anything, right? Models are used as artifacts as part of the development process. Everybody does modeling, whether you do it in your head, or whether you do it using tools, or whether you do it on paper, or whether you actually implement things with it. Modeling is something that you do. And as soon as we put a label on it, so like model-based engineering, suddenly the theoreticians jump up, and there's a theological battle as to who and what is right and so on. In my opinion, like I said, that's a false lead. It's a red herring because what we're really interested in is advancing the state of the art. So let's see what is happening in industry with these technologies. So I've given this talk, actually, I gave it a version of it recently in a company in Austria that is very interested in using model-based engineering for reasons that are very practical, not because they want to be state-of-the-art or anything like that, but because they believe it can help them in some practical way. You notice this picture, by the way. Over here you see a medieval cathedral, which was designed the way that we design software nowadays. Right? We basically build it and see if it's going to stand up, and usually it doesn't until we fix it and so on. But they used actually models as one way of specifying what it is that needs to be built. So they built models of these cathedrals that they were used not only to figure out what to build, but also what it's going to look like, so they communicated with all the people who were interested in what the cathedral looks like using models. But one other thing I want to emphasize here is the word engineering. I'm an engineer by training. one thing that's nice about engineering, traditional engineering, is you actually do a design. You have some ways of validating that the design is correct, and based on that, you actually have a very high degree of confidence that the design will work. And as I said, in software, unfortunately, we're not there yet. The vast majority, and I've had almost, well, over 40 years of experience with industrial software systems, I can tell you, we're nowhere near close to that. Large software systems. I'm not talking about small apps like you have on your iPad or your iPhone or whatever. So what does it take to evolve from craft engineering? There's an interesting book that talks about that very topic. There you can see the reference. I will be giving copies of these slides and passing them around if anyone's interested. And by the way, please feel free to ask questions. If you're upset about something I'm saying, raise your hand. I used to know a friend of mine used to hand out whistles to his audience. So if they objected to something, they would blow on the whistle. Well, I don't have whistles, but yes, you can, if you have something that you're passionate about, we'll have a question period at the end, of course, but if you have something that you think is important to say, please do. So he basically said, okay, these are the things that would characterize a good engineering disciplines. There's a substantial scientific foundation behind it. There's good training, systematic training. We know how to teach the building of engineers, architecture, and things like that. There's the systematic application of the knowledge that has been built up, and I can't emphasize this enough, a sense of professional responsibility. In other words, you, say, as a designer, as engineer, are responsible to whoever the end users are of the system, whether it's a bridge, a house, an airplane, you are responsible. And let's see how we do, at least based on my experience, 40 years in industry. We are starting to build a systematic body of knowledge around model-based engineering. We have a long ways to go, but the good news is there's something emerging from there. This is the job of people, a lot of people here. It's the training. I think there's still a lot more that could be done with the training, but I don't think training is the real problem. This is, in a way, this is related. One of the reasons that people don't do a systematic way of developing software, I'm not just talking about processes, development processes and things like that. I'm talking about the overall approach to designing software in industry. We're far from being systematic about it. People do it differently, different ways. Usually they don't do it in a systematic fashion. So I think we have a lot to improve, but part of that has to do with how they're taught on some of these things. And one of the things I'd like to point out right at the beginning is software development involves programming, but programming is actually a small part of it. Even though you might actually be spending a lot of your time, large percentage of your time is programming, but that is actually a small part of it. There's a lot happening around software development, particularly when you're working on a product that sits there, that gets in the way there. And then there's this one. You know, if you build a bridge, if you design a bridge and that bridge collapses, people go to jail, honestly, if you are negligent. In software, we should be going to jail because there's so much damage happening, literally lots of millions, and it's going to get worse because we're talking about Internet of Things and things like that. There's two things I want you to take away from this talk. One is there's ample evidence, even though this is not something that people are aware of, there's still this question of, is this idea of using models and modeling tools and technologies and is that something that can be applied in industry? The answer is yes, and I'll document that in this talk. And what does it do? The evidence is that yes, it can improve the quality and the productivity. Quality, the quality of the product. Productivity has to do with how effectively you produce that product. That's really what industry is interested in. They're interested in these two things. If you're working on any kind of research that's associated with industrial software, these are the two things you're looking for. Improve the product, the quality, improve the productivity. And if you can do both, that's even better. And that's what this model-based stuff is all about. However, and I won't have much time to talk about that, it's not that easy to introduce this kind of thing because there's a technological, psychological, cultural shift that's involved. Huh. You've heard of Machiavelli, right? Nothing more difficult, more perilous to conduct than introducing a new order of things. Why? Because the innovator has, and we'll talk about that. Who are the enemies of new methods in software? Think about that. I'll give you my answer, again, based on a lot of industrial experience. So here's what I'm going to talk about. What is this thing I call model-based engineering, why it exists, look at some case, some documentation. There's lots now of documentation available. A lot of it, by the way, John Whittle, your new dean, has done a lot of work in this area. He has been always interested in how are these things actually applied. Forget the theory and all the nice stories and the hand waving that I'm doing here. How has industry actually, what's the industrial experience with these things? So I'll give you some examples, 3 case studies, actually more because some of them are overview studies. I'll talk a little bit about what stands in the way. Why isn't everybody doing this? If it's good, why isn't everybody doing it? Look at the reasons, subjective and subjective. I probably won't have time to talk about what is needed, what needs to be done to actually increase the penetration of these kinds of things. Summarize at the end. So, how many people have heard of the Internet of Things? How many people are scared of the Internet of Things? I'm really scared of this thing. Why am I scared? Because these are systems that are of immense complexity that we've never actually attempted before. Yet, we are building these systems and we don't know how to build them. We really don't have a systematic way of building the Internet of Things. And I can tell you from my previous experience with large systems, for example, I worked on the telecom packet switching system, which had maybe 15, 16 million lines of code. And the complexity there was overwhelming. And now we're talking about systems of systems that essentially consist of separately developed, independently designed, and all of these systems. And my point here is that we cannot do it the way we used to do it, because the complexity of what we're trying to do is so much greater. And we are going to have some really serious problems. And why is it? Well, look at this piece of code. I don't know how many of you can see this piece of code. This is actually a piece of, it's called, not objective. It's essentially a variant of C++ used for system on a chip design. So it's a very high level domain specific language. You know what we call this stuff? Code. We call this kind of programming code. Now, why do we call it code? You know what code is, right? It's almost like a secret representation of things. In other words, it's not the most direct way of expressing this stuff. And what it means is that somebody has to mentally translate something which has nothing to do with computers into something that a computer can do. And that's a very technically complex process, and one of the reasons we run into so much trouble with software. It's called code. And the reason it's called code is because we're translating this into something that a machine understands. And the way machines work is not the way people work. Some people are good at that. But in general, it's easy for us to make mistakes. So this is the computing. In fact, what we want to do is raise the level of abstraction. And what is it that we're abstracting out? We're abstracting away the computing technology underneath. The fact that it's computers and then there are bits flying in there and electrons and whatnot. We want to go above that. Right? So I'll give you, this isn't necessarily a very high level. This is, by the way, the UML model of this. And again, I'm not advertising UML here. Like I say, UML is the Fortran of the modeling language community, right? In other words, many mistakes and so on. We didn't know what we were doing, but we produced something, and unfortunately, or fortunately, depending on who you are, it caught on. But believe me, you can take that model there, which is easy. Look at just the fact that there's so much less information here is easier to understand, okay? But if I specify the meaning of those boxes and those lines, I can literally generate all of that. This is one of the applications of this idea of model-based engineering, is that we can automate a lot of the process of translating a high-level specification into a computer program, into code. Let the computer do that, because, to be honest, it's a boring task, actually. And people are not very good at it, and nor are we very productive when we do it. If a machine can do it, let the machine do it. Let's use human power, which is imagination, creativity, and so on, what it's good at, not at translating those pictures into that. That's really what's behind a lot of this. So the essence of model-based engineering comes down to two things, only two things. And you can argue against UML, you can argue against a lot of the tools, possibly rightly so, but you cannot argue against these two things. What are they? One is increasing the level of abstraction. So, for example, rather than coding, if my problem is better expressed using, say, a discrete event kind of a state machine formalism, let's express it in state. You know, this is actually not even going far enough, but, you know, let's get to this stage first. The first time we did this, and I'm old enough, I used to work on aircraft simulators, and when I started, we used to do it in assembly language, on a mini computer. There were no microcomputers there. Mini computer. And then we got this wonderful machine called a VAX that had a fantastic optimizing compiler. And I could do, writing it in Fortran, I could write the equivalent of my assembly language code in 3 days, which would normally take me a month to do in assembly language. So huge improvement in productivity. Unquestioned, the best thing that ever came out of software engineering or computer science is the compiler, which is really what it does is it translates something which is supposedly not machine language into machine language. And the second fact, so you can argue against UML and so on, you cannot argue, this is good. This is unassailable, we need to do this. Question is, you know, what is the right way to do it? And there's some arguments about that. The other one, of course, is increasing the level of automation. That's the compiler. And again, success of that is undeniable. And the need for that is undeniable. So that's, if somebody asks you what this model-based engineering stuff or model-driven development is, it's not necessarily just about code generation, because I can generate documents, I can do things like generate a model from another model which can then be analyzed for things such as, is it going to have a performance level that's acceptable? Is it going to use enough memory? What about battery consumption? Everybody has a mobile phone except me. And I'm sure you're concerned about battery. And I can tell you that the people who design these applications have to worry about, you know, how am I using the battery? That kind of low-level stuff. So there's a whole business of automation that, in fact, I think I have a slide on that. Yeah. Next slide. What can be automated? I'll just go through this quickly. You can do all kinds of design evaluation through formal static analysis. You know, is this a good approach? Before I start coding, will it do what will it have the desired qualities? Will it be fast enough? Will it take enough? Will it fit into the memory? I can maybe simulate something at a very high level. That's a kind of dynamic analysis as opposed to static analysis. I can link parts of my design to other parts of the design through computer linkages, through things such as hyperlinks and whatnot, which you can do with models. You can do things like generate test cases from models a lot more effectively than you can generate them from code. You can do all kinds of model-to-model transformations, like model-to-code being one of the most salient ones, but you can also say, what parts of the system are you interested in? And I will define a transformation so that you see what you want to see. And this is another aspect that's very important, part of model-based engineering, which I think I'm going to have on the next slide. I can generate documents. I can tell you in industry, this is an enormous problem. I was mentioning earlier today, one company that I worked with has 800 documents of a living product. It's actually associated with your mobile phones. Every time they add a new feature, guess what? They have to revisit and understand which of the 800 documents need to be modified. How do we ensure that they're modified consistently and correctly? And if it's all scattered all over the place, believe me, it's a tremendously difficult problem. And each one, any one of these will yield a major quality and productivity improvement if we can automate it. So the essential objective is improve productivity, improve quality. Okay, that's what we're looking at least for me, because I'm an industry guy. So let's see what people are doing. How does MB achieve this? This is what I find a lot. I'm a consultant and I go to a lot of people who are interested in things like UML or modeling languages, modeling tools. And I was in one place, a fairly big company, again in Scandinavia, and the manager was taking me through the development shop and he was saying, no, we don't do this UML stuff because, you know, we don't believe in modeling, it's a waste of time. And as we were going through the offices, on the whiteboards, this is what you saw. You didn't see code. This is a model. Clearly it's a model. So they are modeling. It's only a question, are they using UML, or are they using tools, or are they doing it all in their heads? Okay. And there's a nice quote from Epstein. You know, as soon as you imagine some kind of design or system, you are modeling. You can't imagine all the code of the system that you're planning to build. You imagine it in some very abstract way, very high level way. So let's look at what a model does. You know, this is my definition of what an engineering model is. Selective representation, in other words, I'm not showing everything. It has to be accurate, meaning that it has to be an accurate representation of the thing that it was modeling. It has to be concise so that we can actually absorb the information. And because of that, it needs to focus on a particular set of things that you're interested in. And different people are interested in different things. I mean, you know, for example, people who worry about performance are interested in the speeds of the processors, how many instructions are used and things like that, whereas people who are interested in memory have a set of concerns. And each one would actually like to see a different representation of the same system. So given that, and by the way, this is an example, this is from the 30s. This is a Lockheed Electra, and when they actually tested this stuff using the model, they found out it was unstable. They had to use the wind tunnel and so on. And this model, by the way, doesn't show anything about the electronics, it's just an aerodynamic model. There's an example of selective representation. And they found out, by the way, that this wouldn't fly. and they actually did some modifications by adding some more vertical stabilizers, and it worked the first time. So what is it? Why does this work? One is it reuses the amount of information that needs to be absorbed at a point. It helps us understand, of course. And again, related to understanding, the content, the model has to be adjusted to the purpose which, if humans are the ones that are absorbing it, has to be understandable to humans. Code is not it's understandable to programs, but not to humans. So this is very important. One of the things I learned in doing modeling language design is the information content has to be adjusted. The syntax of your modeling language is crucial. So it's all about reducing complexity through abstraction. Why do engineers build models? They build models to understand. They build models to make predictions. If I do it this way, what will happen? Is this going to work? Is it not going to work? Is it going to be fast enough, etc.? They build it to communicate, to not only amongst themselves and their stakeholders, the people who are interested in the system, they want to communicate with themselves. Believe me, I don't know how many software designs that I did, I finally managed to explain when I was trying to document them. You know, some of your decisions are made implicitly and so on, but then when you're documenting it, you have to capture the rationale, and then you suddenly realize what's behind that. And quite often you end up with a situation, so, ooh, I didn't realize that's what was behind the decision. And it's used to specify systems so that somebody can go and take your model and build it. And these are two very different kinds of models. These are so-called descriptive models which are there for these purposes, and therefore their objective is to minimize the amount of information so that they could be more easily understood, more easily communicated. These models, on the other hand, have to have enough detail in them so that, for example, they are unambiguous, which means that I can maybe generate code from them, for example, or I can analyze them for performance and so on. and therefore they're actually at opposite ends of a spectrum. You know, if this is what we want, very little information here, we want enough information here. Interesting question for modeling language designers: is it possible to design modeling language that satisfies both? I think it is. I've seen examples of that. And here's the difference, right? A descriptive model, you can think of it like, you know, here's a toy of a Batmobile. Here's a prescriptive model, which is a blueprint, and it has a lot more information in there, and so on. Lots of detail omitted. These are not precise enough, but a lot easier to understand. I mean, this is, you know, you have to really look at this and to understand. There's sufficient detail for implementation, but, you know, it's getting difficult to understand. We need both types of models. And furthermore, ideally, we'd like to have a very smooth transition from one to the other. And going back and forth, by the way, going in one direction is never enough. Because, anyways, in software it is sometimes possible, and people in industry are doing it, to actually do this in a, I won't say seamless, but you can use automation to take a model and produce an implementation, and then validate that implementation and say, oh, that wasn't very good, let me change the design, and then work that way through a cycle. So let's look at the industry experience. I'll go through this very quickly because this is mostly data. I just want to give you the sense of what this is. One of the sources of data is actually a study that was done as part of a project by Professor Whittle. And others. I'll go through them, but I'll focus on one of these cases. These are the prominent industrial users of this technology in anger, meaning that these are the people who actually implement things using languages like UML, SDL, and so on. And one of the things you might notice is that it's predominantly kind of real-time interactive system categories. And the reason for this is not because these people like modeling or anything like that, they should, but it's more the fact that their problems are so complex, they need that abstraction that, in order to design these systems. So because real-time and embedded systems have to interact with the physical world, and the physical world is Murphy's Law. Whatever can go wrong will, and you have to deal with it. Okay. So the Motorola study, this is all published. They used the full cycle. They developed a model using this language called SDL, which has subsequently been actually merged into UML. And they did not do any round tripping. What's round tripping? Round tripping means I generate code, usually some kind of skeleton code, then people go and annotate and start coding on top of that generated code. And then supposedly you can go back and use a inverse transform that's going to turn that modified code into a model again. And there's a beautiful analogy. I borrowed this, so I can't take credit for this. Okay, yeah, you can modify this, but then it's not easy to do that. Why? Because people modifying generated code don't care about, say, the semantics of UML. They'll just put in whatever they want, and it's not really practical. Although this is still the dominant way of people using it, but I warn against it. This is a team that had a lot of experience with model-based engineering, so they were very experienced. So this is not necessarily a typical example, although I'm using it as an exemplar of what can be done. What they did was, it was one of the few systematic studies where they did a comparative analysis. They had 5 new features for some of their telecom equipment. They did 2 using model-based methods, and they did 3 using traditional methods. And you'll see how, it's always comparing apples and oranges, but you'll see how they tried to normalize that. So 3 were developed, 2 are using model-based software engineering. There's a reference, you can go find it. Here's what effort in terms of productivity. So this was the development effort for the 3 features normalized, and this was the testing effort required to test it. And of course, this is for handwritten, and this is for model-based. So that's the model-based with auto-coding. And then productivity gains, they measured in terms of, they looked at the generated code that came because it was done, this was done in SDL, this was done in C. They looked at the number of generated assembly language instructions in order to be able to compare these two things. So it supposedly removed the effect of the language itself, and it basically said in terms of how much kilo lines, thousands of assembler equivalent lines of code per source module. And it turns out that the assembly language, now of course you can say maybe these guys were really lousy code generators and therefore they produced a lot of extra code, but believe me, that's not something that their company would have accepted. So in terms of the ability to produce code, they ended up with a 10-time productivity gain, which is probably at the high end these days. They had efficient code generators, real guys that really, really focused. It's just like the assembly, you know, the compiler people. There are some people who are very good at inserting compiler optimization. It's the same kind of problem. They found out it was a lot easier to inspect these things. It was, because they used automated testing, it was a lot less testing effort. They moved a lot of detail that you didn't have to worry about that were actually was inserted by the code generator in terms of how to optimize stuff and so on. And they used simulation. They ran executable models. The quality gains can be seen in this chart. This is the rate at which they uncovered bugs. So you can see, of course, eventually, this is not true, of course. They uncovered 100% of the bugs. You never uncover 100% of, but whatever it is, that 100% that they defined. It looks like these things are fairly close to each other, but look at the timeline here. Look at that particular point there. When they started coding, when they started coding, you'll see that they uncovered twice as many problems at the same point in the development cycle. That's the quality bit. And the productivity in the end, because if you find your bugs early, it really saves you time. This is the defect density that they uncovered, and it's obviously very good on the auto-coded side. But again, don't take this as a typical example. This is a problem, but it shows you, you know, these guys were really good at it. It shows you what can be done. And this was their summary, et cetera, et cetera. The study done by John and his team at the University of Lancaster, you can pick up that study, although I'm not sure if this URL might be broken now. I may have fixed it, I don't remember. The objective was to understand, you know, are these claims about the possibility of you know, MD practices really gaining us some tangible benefits are not true. And to do that, it's a while back now, they had an online questionnaire and they did in-depth interviews with actual people who were experts at this. Now mind you, the sample here is not necessarily representative because they talked to people who were typically successful with this, right? Because people who were not successful with it wouldn't necessarily like to talk to you and expose their. So this is not, you know, there's a bias, significant bias in this. There were 22 professionals with a total of 360 years of expertise. They were focusing on, is it really going to be more productive? Is it going to be easier to maintain? Again, that's a productivity thing, actually. Portability, are these models more easily portable? Are these implementations more easily portable because they abstract away all the technology underneath? And just to summarize some of them, because I'm running out of time quickly here, 74% thought that it did increase productivity for the people who were interviewed in the questionnaire. 7% some people disagreed. They thought it actually took more time, but you know, the bias is heavily in favor of model-based engineering. Is it a good thing? Of the 401 people that had responded, 84% yes. These are practitioners. But a certain category of practitioners that I'm going to talk about in a few minutes. Productivity impact, did it actually improve productivity? If you add these two up, you'll see that it's much better than the Brexit ratio. made easier to maintain software. Again, it's very well in favor. General, was it successful? Yes, again, though there's a bias here. Other notable results, yes, it takes training. It does speed up the response to, when new features come in, it's easier to do that using understanding between stakeholders. It helps as a communication vehicle. If we have models, it's a lot easier to communicate what our intent is, what our designs are. Then there were two SysML studies, one conducted by the OMG, the other one by INCOSE. They focused on SysML, which is the modeling language used in systems engineering. There was a study done in 2009 and another one in 2012 with a significant number of responses. You'll see 134 here, 128 here, just to see what the people who were using SysML thought about it. Here's what people used it for. All the things that productivity and quality. Develop system concepts, speeded up design, improve quality of requirements, or requirements, not just designs, requirements. Why? Because when you have models of designs, it's easier to identify, for example, flaws. Productivity, that's what they were looking for in communication. So this falls into those two categories that I said, improve productivity, improve quality. A lot of it, you know, these are the domains in which these were used. Just in case you're keeping track, that's slide number 39, I have 78. But I'll finish on time. I'll just stop talking. Last year, so they believe this, whoever used this successfully believes they will keep doing it. Which languages they used, SysML, UML, and so on. This, not that key data right now for this talk. The value of model-based engineering, this is a 2009 study. 56% at that time said medium to high value. 4% felt that added no value, which is a nice number. And then in the 2012, I'm going to give the equivalent, large projects and so on. So these are all large, these were not Mickey Mouse projects, these were large projects. Okay, so you have the references for this. If you, what I wanted to do is give you a sense, not just of a single project, but across a range of projects in different languages and different domains and so on. You can check that data, it's all in the references there. Let's look at what, as I say, if this stuff is so good, why isn't everybody using it? Right? Sounds reasonable. Why? My God, if I can improve my productivity by 100% or 10 times, even 1,000%, I'll be better. So one of the questions that was asked in the OMG study was, what stands in the way, and this tops the list. Cultural change. You'd imagine that, same thing over here, by the way, in the 2012 study. You'd imagine that software people are the people who are high-tech, advanced, new stuff. Let's do new stuff. Turns out they're a rather reactionary lot, but what stands in the way? There's three fundamental things. There are all these cultural issues. I'll focus on those for the time, but there are economic reasons. I mean, you have to train people, you have to buy new tools, etc. You have to redo your process, and there are technical issues. The tools are lousy, I can tell that because I've been working on tools for the past 25 years. They're all bad, including the ones I helped develop. But the point of this thing is, it really is less of a technical problem than a contextual problem. There's my Machiavelli quote now. And how does that relate? Who does well under the old order? Who is opposed to this? Can you guess from this slide? This is a nice way of putting it. I find one of the interesting syndromes I find among software developers is that they're so infatuated with the seductive pleasure of programming that in the end the medium becomes the message. It really is beautiful to program, from idea to reality in minutes. You know, I work with automotive engineers. It takes them 3 to 5 years from idea to reality. It's not a very, you know, they don't like that process. Whereas software people, especially programmers, love the process of programming. That's what and they perceive themselves as being not experts in the thing that they're building. They're experts in programming and programming technology. So now let me give you an example. When I started as a young engineer, I graduated in 1972. CAD was, computer-aided design was being used for hardware. It was introduced about that time. You know what? Within a few years, 90% of all the hardware designers wanted to do CAD because it got them to the product faster. And they really were interested in the product. Software has been an uphill battle all along. There's a huge resistance. I'm sure that some of you are students, you hate doing this modeling stuff. And to make things even more tragic, no other engineering discipline has that many practitioners, which means that we have this huge inertial mass to convert. And right now, the only thing I can say is we have to wait until all these people die off, including, you know, people like me. And by the way, I can talk about this because I recognize all of these faults that I talked about. I experienced them personally. So, you know, I mean, these software people, you know, the famous, you know, a man with a hammer, to a man with a hammer, every problem looks like a nail. And these are exactly what we're dealing with. It doesn't matter if I'm building a game, it doesn't matter if I'm building a software for an autopilot or a bank, it doesn't matter, just let me program. Right? Their principal interest is in programming technology. Because that's what they, you know, there's a lot of investment in becoming a professional software programmer. You have to learn not only the languages, the tools, all the libraries, all of that. It's a huge investment, and therefore people perceive them, in my practitioners, perceive themselves as, I'm a Java guy, or I'm a C# guy. I'm not a packet switching guy. I'm not an autopilot guy. I'm a C, you know, just give me the problem, tell me what to do, and I'm going to do it for you. And therefore, one of the interesting things is that you find that these people often are not interested in the product that much. It's not that they're not interested at all, but that's not what motivates them. So if a new technology comes around to do things better, they're not really interested. The most common thing I hear, we can do it the old way. And yes, you can do it, but where's the productivity and the quality? So because they spent so much time mastering, you know, to become an expert, say, Linux programmer, how many people know about Eclipse? Anybody here who's, what a monster! It is a monster. I mean, I work with people. I haven't done any development myself, but I work with people on a daily basis who are developing with Eclipse. The amount of information you have to know just to develop something basic in Eclipse is enormous. You know, people complain about UML being too big. Well, it's nothing compared to what you have to do in order to program in Eclipse. Just enormous complexity in there. And, you know, they're saying, oh yeah, Java is much simpler than UML. Well, yes, Java is, but then, you know, if you want to use Java, you have to know all the libraries, all the tools, how do you debug Java, and so on, and the amount of that knowledge is enormous. So a lot of effort is spent, and therefore, there is very little motivation in moving to new technology. If you're a Java expert and somebody says, we're going to switch from Java to Python, guess what? No, we'll do it, we can do it in Java. And there's 25 million on it, so let's wait for them to die. Management, we have a big problem in industry in the sense that it's a very competitive environment. It's so competitive that if you don't produce in the next quarter what, say, the analysts, the stock market analysts expected you to do, your stock is going to get hit, especially if you're a public company, obviously. And therefore, there's a tremendous amount of pressure to deliver, which means it's all short-term. So industry is fundamentally driven by short-term because of the competitive pressure. It's all about, let's do the next release, make sure that it's on time. That means no time to invest in retraining, retooling, or even thinking about future products. So short-term outlook, and this is a killer. And no manager is going to be rewarded for making the next project successful. You get rewarded for making your project successful. So if somebody says, you know, we really should be switching to model-based methods, tools, whatever, people are going to come and tell you, oh, wait a second. You know, you're going to take these 5 critical people from the project and have them playing around with UML and tools? No way. And project managers, so little incentive to make the future. So there's very little, what I see, and this is a disaster for our industry, this is where we're going to, there is very little support for strategic thinking. Even there are people who are obviously capable of doing that, but there's no real motivation, especially in industry, to do that. And there's the famous burden, you know, so we're going to make this one successful and we'll worry about the future later. Okay, I'll skip some of this stuff. Can you afford not to invest in the future? I don't think so. There's cost involved with development tools, technical challenges, lots of, I like this quote from, although he's been humble about it, from von Neumann. We've reached the limits of this computing technology stuff, 1949. But, he said, you know, statements of this kind tend to sound pretty silly. There are capability challenges, the technologies are unripe, scalability challenges, usability, in particular usability challenges are awful. We're building complicated things with this stuff, okay? Complicated systems require complicated tools. So there's no doubt that there is an essential complexity involved in the tooling. However, unfortunately what we're seeing these days is far too much accidental complexity, and again I won't go into all of these things. Scalability, usability issues, because I want to close off here. So what stands in the way is all these factors, but that basically stand in the way of real advances. And I don't know, can somebody tell me what's common to these 4?
They're gone. There used to be someone.
Exactly. And they did not, and Kodak invented the digital camera. Xerox, personal computer, graphical user interfaces, everything was there. And we know what stopped them, by the way, is that these companies were very successful at doing things, and it's their very success that killed them. Nokia as well, I worked with Nokia. They were not interested in adopting, whereas their competitors adopted model-based engineering and overtook them. But you know, when you have a successful team inside the company, these are often the most dangerous people because they have the power. And because they have the power, they will, and they know what they know, they will try to retain that knowledge and that power, not necessarily with evil intent, but because they're so confident that they know what, you know, they've proven themselves the source of success in the company, and therefore they must be right all the time. I'm going to skip what is needed and conclude. What is needed is a systematic way of introducing. This is interesting to companies. I talk to companies and I give them plans for how people are introducing model-based engineering to overcoming cultural factors. One of those things is institutional. It has to. You cannot introduce this in a skunkworks project. It has to be done systematically. It has to have approval of management. And there's the academic side. We need to teach people some of these things. We need, in particular for me, is system-level thinking. You know, if you find yourself thinking in terms of code about a new problem, you're in trouble. You're not going to design it well. You're thinking at a too low a level. It's like thinking of how do I build the Titanic, but focusing on how do I do the riveting. Lots of research is needed. Okay, let me just summarize here, and I apologize, I took 8 minutes longer than I thought. That's John's fault, he took too long with the introduction. It is a proven method, okay? We really don't need more proof, but it is fraught. You can't just say, let's buy these tools and let's read these books and do it. It's still, unfortunately, each case has to be done individually. So it's not smoke, but it's, I would say 50 to 20% of the companies are using some form of model-based engineering. And we have to solve all those issues. Here's something, and John might not actually agree with these because some of these I took from his papers, but I also added some based on my own experience. You cannot motivate this by the technology. Say, we're going to go and do some advanced stuff. The only reason you want to introduce this stuff is because there's a real business need for it. We have to produce better software at a higher rate. That has to be the primary. Don't say we need to switch to model-based engineering. That's a killer, and it's the wrong reason to do it. You know, not because it's sexy, but because it actually does what it's supposed to. It's important to have management buy-in. In my opinion, you have to have always somebody who is a prime in this, somebody who is willing to take on. It takes guts to do this. Somebody says, I believe in this stuff, and I take, if it fails, it's my failure. It takes guts, and it's not easy, especially in large companies. You cannot sell this to, if you just sell it to management, it won't work. You have to make sure that the people who are going to be using this stuff believe in it and buy into it. This is something I learned from John's study. This came as a surprise, which was don't use it on a small project. It's not important because then people won't try hard enough.